When the Apollo 11 astronauts walked on the moon, they let a specific mirror, a laser reflector, sit on the desolate lunar surface. By timing how long it takes a laser pulse to hit that mirror and return, astronomers found a precise physical measurement. The moon is moving away from Earth at a rate of 3.8 centimeters per year. This diagram shows the classic explanation: tidal friction. The moon's gravity pulls Earth's oceans into a bulge, creating an offset angle that breaks our planet's rotation. Through conservation of angular momentum, this lost rotational energy accelerates the moon into a higher, more distant orbit. For decades, this near-perfect exchange has been treated as the reliable clockwork foundation of planetary dynamics. But projecting that 3.8 centimeter drift backward reaches a 0 point far too quickly. According to this constant rate, the moon should have collided with Earth just 1.5 billion years ago. The geological record says otherwise. Evidence from ancient sediments proves the Earth and moon have safely coexisted for over 4.5 billion years. Since that collision never happened, the classical model of constant tidal friction is clearly an incomplete description of the past. To find the missing variable in this planetary timeline, scientists have to check the actual data preserved in the Earth's crust. Investigation of the ancient Earth-Moon system relies on deep-time geological archives. Fossilized corals and tidal rhythmites record daily and monthly cycles, acting as biological calendars from billions of years ago. This scatterplot shows how the length of a day has changed over time. By analyzing data points from 3.2 billion years ago, geologists discovered that Earth was spinning much faster, with a day lasting only 13 hours. At the same time, this graph traces the historical Earth-Moon distance. These records show that 3.2 billion years ago, the moon was hovering at roughly 70% of its current distance. These rocks provide the only empirical data points we have to test our theories of orbital evolution over billions of years. When physicists run the angular momentum calculations using this 3.2 billion-year-old rock data, the results show a massive discrepancy. The math reveals a stark anomaly. 3.2 billion years ago, the rate of Earth's rotational loss exceeded the moon's orbital gain by nearly a factor of 3. The gymnast analogy fails here because the Earth-Moon system isn't a rigid body. They are separate masses coupled only by weak tidal forces that lose energy to friction in the oceans and crust. In this soft, deformable system, there is no physical requirement for a direct one-to-one momentum transfer. If the Earth has been bleeding out rotational energy that the moon isn't catching, where is that energy going? The dark matter field fluid hypothesis suggests space is filled with a fluid-like medium. Under this theory, Earth's rotation creates drag against this medium, dissipating angular momentum into the dark matter itself. The dark matter field fluid model accounts for the observed discrepancy by treating the missing momentum as a direct interaction between planetary rotation and the dark matter medium. This means the perfect one-to-one momentum exchange we see today is a temporary coincidence of our specific geological era. Earth's rotation will continue to slow as it bleeds energy into the void, while the moon continues its long drift away from us. The most dramatic evidence of this drift is the total solar eclipse. We live in a period where the moon's size and distance allow for this perfect alignment, completely blocking the sun's disk. But as the moon recedes, it appears smaller in our sky. In roughly 600 million to a billion years, it will be too small to fully cover the sun, ending the era of total eclipses forever. We exist in a brief window where this alignment is not only visible, but serves as a tool to measure the invisible forces slowly pushing our worlds apart.